The decibel operator is ubiquitous in electrical engineering. We see dB all the time when we are expressing different kinds of values, things like gain, but also in terms of power, there are decibel operators. But despite this popularity of the decibel operator in electrical engineering, there's quite a bit of misunderstanding and misuse of the operator and what it means. And so let's go over and talk about the decibel operator. You may think that you know about this and know all there is to know about it, but hopefully this presentation will enlighten you to a few more facts or maybe some misconceptions that you had. The decibel operator is pretty simple. It's a mathematical operator, and it's defined uniquely in one way, only one way, and that is the decibel operator is 10 times the log base 10 of some unitless value x. And I emphasize the value of x must be unitless. We can't go through and take the log of some value that has units of energy, for example. What would the result mean? What would be the units of that result? Certainly wouldn't be energy if we take the log of that value. The only way that this can be useful to us then is if x is a coefficient. It is a unitless value. And of course, there are many values that in electrical engineering that are useful, values that are ratios or coefficients. And of course, amplifier gain may be chief among them. Since we're talking about microwave amplifiers, gain is defined as the ratio of the absorbed power by a matched load at the output of the amplifier attached to the output port, divided by the power available from a matched source at the input of the amplifier. And again, this is different than other non-microwave amplifiers, where we might define gain as the ratio of the power absorbed to the power delivered by the source. In this case, again, it's the available power of the source. And again, it's the absorbed power of a matched load, specifically for this load. Now, this ratio, of course, then becomes a coefficient. It is unitless, and we can express it in terms of gain. And frequently we do. Almost always we will speak of a microwave amplifier gain as something like 13 dB or 17 dB or 6 dB, meaning that the gain has been expressed using the decibel operator. So let's say the gain of amplifier is a value greater than 1, which of course is typically the case for amplifiers. Otherwise it wouldn't be amplifying anything. And when we have a gain greater than 1 and we express it using the decibel operator, we find that the gain then is a positive value. If we were to have a gain less than 1, a gain that, 0.2, something like that, and we expressed it with a decibel operator, we would find the result would be negative. And therefore, when we have a gain that's precisely equal to 1, then the gain has when expressed with the decibel operator, has a value of 0. Now, I use example of gain here for these situations, but again, this is true for any coefficient we might use in the decibel operator. If the value, the coefficient, is positive with the decibel operator, if the value of the coefficient is greater than 1, rather, when expressed with the decibel operator, will become positive. If the coefficient value is less than 1, expressed with the decibel operator, the value will be negative. And then, of course, if the coefficient is equal to 1, when expressed with the decibel operator, will have a value of precisely 0. Now, one value of gain, or one value of the coefficient that we should consider is if it's equal to 10. If it's equal to 10, we express it in the decibel with the decibel operator. The result there is likewise 10, and this is because 10 log 10 is equal to 1. And so oftentimes, or sometimes I should say, I find students that will take this one statement, this case where gain is equal to 10 results in a gain of 10 dB, quote unquote, take that case and try to extend it such that if the gain is 20, then the gain would be 20 dB, or if the gain was 30, it would be 30 dB. And of course, this is not correct. If this were true, there would be no point in using the decibel operator. The distinction between the gain and its gain expressed with a decibel would be a distinction without a difference, and so we wouldn't bother. So make sure you don't make this mistake. So this is perhaps the most important mathematical relationship if we're using the decibel operator, one to keep in mind. And that is if I have, we apply the decibel operator to a value which is a power of 10 to the nth power, we could rewrite that as pull out the n out front using the identities of logarithms. Pull it out front, and we can rewrite it in this form, n times 10 log 10 of 10. But 10 log 10 of 10 is 1, and therefore this result simply becomes 10 times the integer, or I should say the value n. It doesn't have to be an integer value. This result is most commonly used when we take our coefficient and we square it. If we take 10 log 10 of x squared, for example, that would turn into 2 times 10 log 10 of x. And of course, 2 times 10 log 10 of x we can also write as 20 times log 10 of x. And this is where the confusion arises, where sometimes students or engineers will say that there are two definitions of decibels. Do we use the 10 log 10 or do we use the 20 log 10? Well, let me say again, this unambiguously, the decibel operator is 10 log 10 of some coefficient value. It's never 20 log 10. Now, frequently we will go through and apply the decibel operator to a coefficient squared. Apply 10 log 10 to x squared. And yes, if we do that, we could rewrite it correctly mathematically as 20 log 10 of x. That is true, but it's not the decibel operator applied to x. That result is the decibel operator applied to x squared. So make sure that you understand that. This frequently comes up when we talk about the voltage gain of a low-frequency amplifier. The voltage gain of a low-frequency amplifier can be positive or negative. In the case of time harmonic analysis, it can be a complex value. So how do we express the voltage gain using a decibel operator? We can't put negative values into our log. We can't put complex values really into our log. Sort of can, but not in a way that would be physically meaningful to us. So typically what we do is we take the gain, the voltage gain, and we take the magnitude squared of that voltage gain, and that turns it into a real positive value. And that we can apply the log operator to. Keep in mind that the magnitude squared of our voltage gain is likewise unitless. It is a coefficient, so we can apply the decibel operator to that. And so we take 10 log 10 of the magnitude squared of the voltage, and we get a result. And that is the magnitude squared of our voltage gain in decibels. Yes, we could have mathematically got there by taking 20 log 10 of our magnitude of our voltage. All right, but the result again is not the magnitude in decibels, it is the magnitude squared in decibels. And this is something that is done, in my view, incorrectly over and over again in many textbooks. When it comes to voltage gain, they'll say the magnitude in decibels, when in fact what they really mean is the magnitude squared in decibels. They would say, well, we use the decibel operator that's defined as 20 log 10 log base 10, but again, that is not a decibel operator. 10 log 10 is the decibel operator. Oftentimes we apply it to values that are squared, and yes, that then can be calculated as 20 log 10, but it is still the value squared expressed in decibels. All right, so if we have a value of gain that we can express as 10 to the nth power, then we can immediately say that that value expressed with the decibel operator is 10 times whatever that value of n is. Now, remember, any value of gain we could express in this way. Any value, 26.37, we could write as 10 to n, where n is some value. It wouldn't be an integer value, but it is a value. And if we know that value of n, we simply multiply it by 10 to get the value of gain in decibels. Of course, in the case of 27.6 or whatever I said for gain there, if I want to know the value of n, I'd find the value of n by taking the log of that 26.7, which essentially is what we do in the decibel operator. So that would be helpful. Where this is helpful is where we don't really need to take the log to determine what this value of n is. And that would be the case where n is an integer. We know that if we have a gain of 100, that's the same as 10 squared. A gain of 1,000 would be then 10 cubed, and so forth. And so if I do have, let's say, a gain of 1,000, 10 to the third power, I can immediately determine that that gain, when expressed with the decibel operator, is 30. Take the integer and multiply by 10. And what this shows here is that the gain, when expressed in decibels, is really an expression of the order of magnitude of that gain. Every time the gain goes up by a factor of 10, one order of magnitude, the decibel result then will increase by a value of 10. If we are at a gain of 10 and then go to a gain of 1,000, we've gone up 2 orders of magnitude. Our resulting gain will increase in decibels, will increase by a value of 20. Look then at this list of values for gain that are distributed over several orders of magnitude. The first case we're looking at gain is 0.01, and then we multiply it by a value of 10, a factor of 10, increase it by 10 times, and we get 0.1. Notice that's 10 to the minus 2 to 10 to the minus 1. Well, minus 2 times 10 is minus 20. That is the value of our gain of 10 to the minus 2 when expressed with the decibel operator. We increase the gain 10 times, and we find the resulting gain increases from minus 20 to minus 10. We add 10 to minus 20 to get a minus 10. We say we increase 10 dB in the gain when expressed in decibels, when our gain itself increases by a factor of 10 times. And this continues. When we go from 0.1 to 1, the result in decibel goes from minus 10 to 0. Again, we're adding 10 to the previous answer. If we multiplied, increased by a factor of 10, the original gain itself. So 0.1 to 1, 1 to 10, 10 to 100, 100 to 1,000. We're increasing the order of magnitude each time, and the result is, when we look at that gain in the decibel operator, that we increase the value of the result, not by a factor of 10, but by adding 10 to it. 0 to 10, 10 to 20, 20 to 30. And so what we see here is gain, or decibels, I should say, really give us an order of magnitude, an idea of the order of magnitude by the number that results. And that's why we use decibel operators so frequently in electrical engineering. We deal with values that have a huge dynamic range frequently. For example, a receiver, a microwave superhet receiver, frequently will have a dynamic range where it can receive signals anywhere from 1 milliwatt all the way down to 1 femtowatt. And so we're looking at dynamic ranges of 100 dB or 120 dB, meaning we have a factor of the smallest to the highest of 10 to the 10 or 10 to the 12. Huge variation from the largest to the smallest. And this happens frequently, and that's why we use decibel operators so often in, not the only reason, but one of the reasons we use decibel operators so often in electrical engineering is because the value really tells us the order of magnitude. Are we talking values of 10 to the minus 6th or 10 to the minus 10th or 10 to the minus 4th? What is the value? Well, we can tell that directly by the numerical value of the resulting decibel operator. So, for example, if we had a value of gain when expressed in the decibel operator, rather in its teens, that means we have a gain that is in the tens, somewhere between 10 and 100. 20-something, 30-something, 40-something in terms of the actual gain will always result a gain when expressed in decibels in the teens. 12 dB, 15 dB, 18 dB. If we have a gain when expressed with the decibel operator of in the 20s, that means the actual gain itself is in the hundreds. In this case, 500 results in a gain of 27. Again, that first digit there, 20, tells us that the gain is going to be somewhere in the hundreds. If we have a gain in the 30s, when expressed with decibel, that means the actual gain is in the thousands. Some more examples. If we have in decibel gains in the 40s, that indicates a real gain. In the tens of thousands, if the gain in decibels is in the 50s, then we have a gain of in the hundreds of thousands. And if we have a gain with respect to the decibel operator in the 60s, that means we're talking about a gain in the millions. So again, this first digit, 4, 5, 6, really points to the order of magnitude. 10 to the 4th, 10 to the 5th, 10 to the 6th. And that's the useful thing about decibel operators. We have such high dynamic range, again, of so many values, that really we are, to a first approximation, just concerned about the order of magnitude. How big is it? Are we talking nanowatts, microwatts, femtowatts? That's what, no pun intended, that's what the decibel operator can tell us. Consider now what happens if we want to make the reverse operation, the inverse operation. Let's say we know that the gain of an amplifier is, when expressed in decibels, is 54. The gain, in other words, is 54 dB, we say. What is the actual gain before we applied the decibel operator? What is the the actual value of G here? We determine that with the inverse decibel operator. And this is a simple mathematical inverse here. I'm just go ahead and write this down just to complete things. And I write this as the notation is dB to the minus 1, which is not 1 over the value of dB. It is the inverse operation, is what I'm trying to say here. What is the inverse operation? It is something where we take the value of gain when expressed in dBs and we put it into that operator, and out pops the actual value G of that gain. Of course, I can use G here, but this would be true of any coefficient that we apply the decibel operator to. Invert the decibel operator, and we come up with this result here. So it's 10 to the power, which is the value of gain in decibels divided by 10. And again, it doesn't have to be the gain in decibels. It can be any coefficient here. Example, then, our 54 dB gain amplifier, if we put that into our inverse operator, 10 to the 54 divided by 10, in other words, 10 to the 5.4, take your calculator, you find we get a value of 250,000. Now, we can always go through and do this to get our inverse operation. But it turns out for most values of gain, any integer value of gain in decibels, we can do this inverse operation very quickly without having to use our calculator. And this is a very important skill and knowledge to have if you're a microwave engineer, if you're a radio engineer. Typically, they can go through and do these things without requiring a calculator. They can do it almost instantaneously because they have this knowledge that we're about to discuss. So to see what that knowledge is, we're going to add a second identity that is about as important as the first one. The first one being that if we had a situation where, well, the first one was that the decibel operator applied to 10, of course, gave us a value of 10. In this case, we're going to consider what happens when our gain is 2, our coefficient is equal to 2. If we apply the decibel operator to that, it turns out we get a value that is very, very close to 3. It's actually, I think, 2.997 or something like that. I can't recall. But it's close enough to 3 that in microwave engineering, we call this 3. And again, this is very important here, that this becomes the value we use in microwave radio engineering. The decibel operator applied to 2 gives us 3 dB. If this value were to be 1 over 2, we would find that would be a minus 3 dB. And you've probably heard about 3 dB bandwidths and the like. And that comes from this decibel operator on 2. Again, we don't go through and say we have a 2.997 dB bandwidth. We talk about it as 3. So I say this is approximately equal to 3. In electrical engineering, it's exactly equal to 3. All right, we just use 3 without any shame or reluctance, even though we know it's not exactly the right answer. It's close enough in all of our applications. All right, here's actually the second identity that we were speaking of. We go through, and if we have a value of gain that we can write as 2 to the nth power. And of course, every value of gain we can find some value m that will satisfy this. So we write it as 2 to the mth power, and of course from the identity of the log operator, we can pull this m out front here. And so this is equal to m times 10 log 10 of 2. But 10 log 10 of 2 we just found is equal to 3. Again, approximately 3. We're going to go ahead and say exactly equal to 3 for our electrical engineering purposes. And so the result here is 3 times n. Anytime we have a gain, we can express as 2 to the nth power. We can immediately say that that value of gain, or that coefficient, is equal to 3 times m. Now, how do we find the value of m? Generally speaking, if I said, again, I had a gain of 7.6, I could rewrite that as 2 to the m power, and I could find the value of m, but to do that I would have to go through and take the log of 7.6, and so, again, that's what really this operator already does. So this is useful to us then, really, when we can express our gain as an integer power of 2. In other words, if the gain is 2 or 4 or 8 or 16 or 32, 64, all of those, we can go through and immediately convert then the gain into its decibel representation simply by taking that value of m and multiplying by 3. The value of gain of 2 then would be a value of 3. 2 to the 1 is a value of 2, and then we multiply that 1 by 3 and we get 3. 2 squared would be 2 times 3 or 6. 2 to the third would be 3 times 3 or 9, and so forth. And so this is a very important identity that we want to be able to use. And of course we can go both directions. If we know the gain, write the gain as an integer multiple of 2, we can immediately express that gain in decibels without having to pick up our calculator and do log. Or conversely, if we have our gain, which is a multiple of 3, a gain of 3, 6, 9, 12, 15, 18, so forth, you can immediately go through and say, well, I know that gain by this expression. The gain in decibels is equal to 18, for example. Well, that's 3 times 6, and so a gain of 18 is equal to 2 to the 6th power. So here are some examples, and this is very similar to the list that we provided when we talked about powers of 10. In this case, gain, or a coefficient, is going to double each time. We start at a value of 2 to the minus 3, 1 over 8, and then we go to 1 over 4, and 1 over 2, and then 1, and then 2, 4, 8, 16. Each time we increase by a factor of 2. Our gain we can write then as 2 to some integer power, and that integer allows us to directly determine the resulting gain when expressed in decibels. And when we do that, we find that the value when expressed in decibels increases by a value of 3. Not by a factor of 3 times, but by a value of 3. From minus 9 to minus 6 to minus 3, 0, 3, 6, 9, 12. And so we see a similar situation that we had when we had powers of 10. Every time our gain increased by a factor of 10, the gain in decibels increased by a value of 10. We added 10 to it. In this case, every time our gain increases by a factor of 2, the gain in decibels increases by a value of 3. We add 3 to the previous one. And this relationship, again, is very important to understand. So spend some time looking at this and thinking about it. Now, we're going to combine the two identities that we've discussed here into sort of one mega identity that is going to be very useful to us. And this identity will encompass the previous two that we talked about. We're going to now look at a situation where we can write gain, or our unitless coefficient, is equal to 2 to the nth power times 10 to the nth power. Now, any value of gain can be expressed in this way, and in fact, there are multiple solutions there. There's no unique solution for m and n. If we see a gain, again, is equal to 7.6, there are many different ways that we can write m and n to get 7.6. So this seems to be a step backward, a step toward ambiguity here. But if we constrain this to say, if our gain can be written in this way where m and n are integers, then we have something. We have an ability to go through and directly determine that gain or convert that gain into its decibel value with the following identity. So let's see how we do that. So we take 10 log 10 of this result, 2 to the m times 10 to the n. And of course, when it comes to logs, log of x times y is equal to log of x plus the log of y. Again, I say that again. Log of x times y is the log of x plus the log of y. That's a very important identity to keep in mind when you're using the decibel operators here. So we can separate it in this into this form rather. And now, of course, we have 2 to the m, which we can pull the m out front, and 10 to the n, which we can pull the n out front. And so these are simply each of the two identities that we had prior. We know this is equal to m times 3, and this is equal to n times 10. And so we have a situation now where if we have gain expressed in this way, we can determine its value in decibels by simply taking 3 times the value of n and 10 times the value of n. How is this helpful? Again, since we have no unique solution here, it generally is not, unless we have m and n are integers. And in that case, m and n, if they are integers, there is just one unique solution. And so we can go through and use this to find the value of gain in decibels. And so this is, again, the mega identity. And this is going to be very useful because it turns out for every integer value resulting the dB of gain, 10 dB, 11 dB, 12 dB, so forth, every integer value can be expressed in this form where m and n are indeed integers. And so we can go back and immediately determine the gain. We can do the inverse operator very quickly if our gain is expressed as an integer value. And that's typically the case. Rarely do you see an amplifier where they say, well, the gain is 32.3 dB. It's either 32 dB or it's 33 dB. And so we can always go through and convert that back to the value of gain if we deconstruct 33 in the correct way. Hopefully you can see how to do that. 33 is 3 times 1 plus 10 times 3. All right, that would give us 33. So we get 2 times 10 to the third power. In other words, we get 2,000 as the gain. A gain of 33 dB is a gain of 2,000. Let's do another example. Let's say we have some gain and we express that gain in decibels, we get a 7. So gain is 7 dB, we would say. We can write 7 now as equal to the value of 10 minus 3. And because we've written as 10 minus 3, we've written in a way that is aligned with the previous identity. 10 times 1 plus 3 times minus 1. So m is equal to minus 1, and n is equal to 1. If we insert that into our identity, then the gain must be equal 2 to the minus 1, or 1/2, times 10 to the 1, or 10. In other words, we get 10 divided by 2, or 5. If we say our amplifier has a gain of 7 dB, what we're really saying is that amplifier has a gain of 5. Notice we did not have to take out our calculator. We did not have to determine any logs or take any power other than the simple integers to get that result. So let's continue and try to do this for every integer value of gain when expressed in decibels. And again, it's not that the gain is an integer value. It would be a situation where when expressed in decibels, it would be an integer value. So we're going to go through and look at the gain when expressed with the decibel operator as 0, 1, 2, 3, 4. In other words, 0 dB, 1 dB, 2 dB, and so forth. And we can find for each one of those a solution for the identity where we have 3 times m plus 10 times n. For 0, of course, m and n are equal to 0, and the gain, therefore, that results is equal to 1. But, of course, we knew that. A gain of, when expressed in the decibel operator 0 dB, means a gain of 1. For a gain of 1 dB, 1 can be written now as 10 minus 9. So we have 3 times minus 3 plus 10 times 1. So it takes maybe a little bit of thought to figure out what these values would be, the solution for m and n under these conditions. M is equal to minus 3, n is equal to 1. We insert that in here. We get 10 divided by 8, or 1.25. For a gain of 2 dB, that is going to be 12 minus 10 is equal to 2, and that would result in a gain of 1.6. 3 is 3 plus 0 here, so that's a pretty straightforward one. And of course, we know that result is going to be 2. Remember, this is exactly equal to 2. Here, don't use your calculator, just use your identity or approximation that we always use in electrical engineering, which is 10 log 10 of 2 is equal to exactly 3. A gain of 4 dB results in, we can write as 10 minus 6 is equal to 4, which gives us a gain of 2.5. Continuing then with a gain of 5 dB, 5 would be 15 minus 10, so therefore a gain of 3.2, m of 5 and n of minus 1, all right, will give us 3.2. 6 dB is 6 plus 0, 6 plus 0, which then gives us a gain of 4. Again, each time our gain goes up by 3 dB, our gain increases by a factor of 2. So we go from a gain of 2 to a gain of 4 when we go up 3 more dB. 7 dB is 10 minus 3, or a gain of 5. We've seen that before. 8 dB is 18 minus 10, which would be 6.4 as the result. 9 is 9 plus 0. Again, we've gone up another 3 dB. From 6 to 9, we've gone up 3 dB. So the gain goes from 4, multiply that by 2, and we get 8. And then finally, 10, we've seen before, gives us a gain of 10. So that might seem to be not very helpful. We've gone through and we determined the solution for all the gains in decibels between 0 and 10. But what about a gain, that are in the teens, 17 dB or 12 dB? What about a gain of 23 or 37 or 41 or 58? How do we go through and find the resulting gain from them if we, again, expressed in decibels? It seems like this would be a ponderous exercise to find the solutions for all of them. But it turns out it's not. Once we know all the answers between 0 and 10, we can determine then the resulting gain for any value. And the key thing here is a situation where anytime we increase our gain value by 10 or decrease it by 10, we know that we're simply changing the actual value of gain by a factor of 10. We go up 10 dB or down 10 dB, we add 10 dB to our answer or subtract 10 dB from our answer. The result is going to be a change in order of magnitude of exactly 1, of a factor of 10. And so let's just show this. If we have 5, we know that results in a gain of 3.2. If we have 15, we could go through and recognize that, here for 5, we had 15 minus 10. And now for 15, we have 15 plus 0. And that will result in a gain of 32. 25, now, instead of 10 times 0, we have 10 times 1 here, 15 plus 10, or 25, and that will give us a gain of 320. Likewise, 35 is 15 plus 10 times 2, and that will give us a gain of 3,200. Look what's happened each time. We've increased the value of the gain in decibels by a value of 10. And the result then is an increase in the gain itself by a factor of 10. And so we can do this with any of the results from the previous 2 pages. If I know the gain of the amplifier is 7 dB, then I know the gain of the amplifier when it's 17 dB or 27 dB or 37 dB. All I have to do is take the previous answer and multiply it by 10, increase it by an order of magnitude, essentially just shift the decibel point over one place. This is true if we are increasing by a value of 10 dB each time, or if we are decreasing by a value of 10 dB each time. So for example, if I go from plus 5 dB to minus 5 dB, the result would be 0.32. If I go to minus 15 dB, it would be 0.032. Every time we go down by 10 dB, even as we move into the negative values, again, we shift the decimal places. If we're decreasing by 10 dB each time, the decimal place shifts to the left. And from this, we can fill out the entire values of our decibel results if they are integers. And typically, good microwave and radio engineers will then be able to tell you exactly what the gain of an amplifier is, or any expression that uses the decibel operator. If somebody says my gain is 47 dB, what is that? What is the actual value of the gain there? They'll be able to say, well, 47 dB is 10 to the 5th divided by 2, or in other words, 50,000 would be the gain. They can immediately go through and do that. So, and it's not that hard to figure this out once you kind of go through and think about it and remember these values. It's easy to go back and forth, and it's helpful for even engineering students to be able to do that. You don't have to pull out your calculator each time and fat finger a button and get the wrong answer. You can go through and write down the answer directly.